So the next very popular scheduling algorithm is called as a round robin scheduling algorithm. So I'll explain this algorithm with this example, but before we go there, so this is a preemptive. So let's understand a couple of important concepts as far as round robin or RR as it is sometimes called as, right? So this is also sometimes referred to as preemptive. So this is also sometimes considered as a preemptive first come first serve. Remember that your first come first serve does not have any problem of starvation, which some other algorithms do have, like shortest job first, etc. Right? So since so this is sort by default FCFS or first come first serve is a non-preemptive algorithm. So round robin is also sometimes referred to as preemptive first come first serve algorithm. Right? So here there is a very interesting twist here. So what it does here in round robin is there is a concept called as time quanta. So there is a concept called as time quanta or time slice. So what we do here in this case is, given CPU, we force each process to be allocated to the CPU only for a specific units of time. For example, imagine if I choose my time quanta to be 2 units of time, then any process can hold on to the CPU at most for 2 units of time, not more than that. Okay. So let's try to understand how the whole thing works. Again, this is very interesting concept, and round robin as a strategy is not just limited to operating systems. This is also used in computer networks for a bunch of algorithms. So round robin as a strategy is a very common strategy across computer science. It's used in operating systems, computer networks, etc. And this is very popular in multi-user, multi-programming. Sometimes it's also called as time sharing systems, right? So let's understand this example. So some of these computing systems are called as time sharing systems because the CPU is shared by multiple processes or multiple users, right? So your multi-programming, multi-user time shared systems, some of them do use round robin as a strategy to ensure that we don't have, again, one of the biggest advantages of round robin is that every process gets its turn. There is no starvation here. That's very, very important, right? So this is starvation free. So this is starvation free. Now let's understand how the whole thing works. Here, let's assume I have my ready queue here. This is what I have in my ready queue, and this is my Gantt chart. Okay, let's write the Gantt chart also. Maintaining your ready queue, maintaining your ready queue is very important to understand how everything works, right? So this is my CPU Gantt chart. So let's assume I'm at timestamp 0. At timestamp 0, only process 1 is in my ready queue. Only process 1 is there. So what is my time quanta? My time quanta is, let's say, 2 units of time or 2 seconds, which means no process can stay with the CPU or no process can control the CPU or have ownership of the CPU for more than 2 seconds. Okay, so I'm at timestamp 0. My ready queue only has P1. Okay, so P1 gets scheduled now. Once P1 gets scheduled, for 2 seconds, I can't do anything. Remember, for 2 seconds, I can't do anything. So this will stay here for 2 seconds, which means its burst time will reduce to 2 now. Now within these 2 seconds, what happened? Your P2 also came into the queue. Remember that within these 2 seconds, your P2 came into the queue. Again, this P1 is removed from the queue and it is scheduled, right? So P1 is removed from the queue. Okay, so let me cut it this way. Okay, P1 is removed and it is scheduled for 2 seconds because the time quanta is 2 seconds, right? While P1 is running on the CPU, what happened? P2 got added to the ready queue. P3 also got added to the ready queue. Look at this, P3 also got added. Now we check whether P1 has completed or not. P1 hasn't completed because it requires 2 more seconds of CPU time. Since it's not completed, what do? We add it to the end of the ready queue. We add it to the end of the ready queue. So since it's not yet over, we add it here at the very end. Look at this, at the very end, after all the processes which came till now, after they have been added, since P1 hasn't yet completed its execution because it requires 2 more seconds of burst time, we add it to the end of the queue. Okay, now we go to the front of the queue. So let's assume this is the front. Let's assume this is the front and this is the rear of the queue, right? This is your first come first serve type of queue, right? A standard queue in data structures, right? So now I have my P2 which I'll process. So P2 gets scheduled now, right? P2 gets scheduled for 2 seconds. Okay, which means my total time is now 4 seconds. So P2 gets scheduled for 2 seconds. So 3 more seconds of burst time are still left. While P2 is being executed, see, look at this. We remove P2 from the queue and schedule it, right? While P2 is running for these 2 seconds, what happened? P4 got added here. Look at this, P4 got added to the queue. P5 also got added to the queue. Look at this, while P2 was running on the CPU, P4, P5 got added to the queue. This is very important, P4 and P5, because their arrival times at 3 and 4 respectively, they got added to my queue. Now P2 hasn't yet completed processing, so P2 gets added to the queue at the very end. So P2 gets added because P2 hasn't yet completed, right? Very important here. Okay, now what is at the front of the queue now? P3 is at the front of the queue. So P3 gets removed from the queue and P3 gets scheduled. Again, P3 also gets scheduled only for 2 seconds here. Okay, so now what happens? P3 is left with 4 more seconds of compute required. 4 more units of time it still needs, right? So what is my total time now? Sorry, I need to write 6 here instead of 2 because 2 seconds got added here. I'll have to fill this as 6 now. Now at 6 units of time, what happened? P6 also got added to the queue. Look at this. Remember that P6 also got added to the queue now. As P6 got added, P3 also finishes 2 seconds. Look at this. P3 finishes the 2 seconds, but P3 is still left with 4 more units of time that it requires on the CPU. So P3 gets enqueued here. P3 just adds itself to the queue. Okay, this again, we start removing the processes from this side. We keep adding to the rear. We keep removing from the front, just like any other queue in data structures, right? So, okay, so let's keep, again, just remember that this is the front and this is the rear. That's very important to remember. Okay, so now what happens? My P3 also got added. Now, what is the first process? P1 is the first process, right? So P1 gets removed here. Now P1 gets 2 seconds. Look at this, P1 gets 2 seconds, right? So P1 got 2 more seconds. So P1 does not require anything else. So P1 completes. Because P1 completes, it does not add itself to the end of the queue. Because P1 completed, right? So perfect, very good. Now, what is the next process? P4 is the next process, right? So it looks at P4. The P4 gets the CPU for two units of time because the time quanta, the time slice here is 2 seconds, right? So P4 gets it for 2 seconds, which means P4 still has 1 more second of compute required. So since it still has some more compute that it needs to perform, P4 adds itself to the queue at the very end, right? Till now everything is cool. Now P4 also got removed because we scheduled it. Now comes P5. Okay, so we schedule P5. So let's schedule P5 here. So P5 gets 2 units of time. So at the end of it, P5 still has 2 more units of time that is left. So P5 adds itself to the end of the queue now. Look at this. We are just adding anything that has some more compute or burst time remaining. We just add it to the end of the queue. And we keep removing from the front of the queue. Next comes P2's turn, right? So P2 requires 3 units of time, but we cannot give more than 2 units of time to anyone, right? So this takes 2 units of time. So this takes 2 units of time. So this is still left with 1 more unit of time. Since P2 still requires 1 more unit of time or 1 more second of CPU, we add it back to the queue here. This is very, very important, right? So P2, we processed it. Next comes P6. Look at this. Here is a very interesting case, right? We removed P6, but P6 requires only 1 unit of time. The maximum time that any process can hold on to the CPU is 2 seconds. But if it is less than that, that's okay. So P6 now holds on to the processor only for 1 second. This is very important because it does not need 2 seconds, right? So 1 second it completes. So it doesn't add itself to the end of the queue. So P6 is completed. Next comes P3. Look at this. Next comes, let me change the color here. Next comes P3. So P3 requires 4 units of time, but I can only at most give, so P3, I can at most give 2 units of time to it because my time quanta is 2 seconds, right? So P3 is still left with 2 more seconds. So P3 adds itself to the end of the queue, right? Because P3 is not yet complete, right? Next comes P4's turn. P4 requires only 1 unit of time here. So we remove P4, P4 requires only 1 more unit of time. So P4 completes now. Very good. Next comes P5. P5 requires 2 units of time and we can give 2 units of time because my time quanta is 2, right? So I have P5 here. P5 takes 2 units of time. It completes execution. Because it completes execution, it does not add itself to the end of the queue. That's very, very important, right? So now what happens? P5 is done. So P5 is also done. Now I'm left with P2. P2 requires 1 unit of time. So we execute P2 for 1 unit of time. So P2 also completes. Now P3 requires 2 units of time. So P3 also completes. Only P3 is left. P3 requires 2 units of time. So we assign P3 to the CPU and we give it 2 units of time. This is how your Gantt chart looks like. Look at this. In this case, every process is getting its turn. Just because a process has too much of burst time or its arrival time is very recent does not necessarily mean that it doesn't get its turn. This is starvation free because, again, this is called round robin, because we are going in a roundabout fashion, right? We're going like a queue, right? We first pick something, we execute it on the CPU. If it is not yet complete, we add it back to the queue. That's what we are doing, right? If it completes, we are done. So a process can go from the front round back to the back, right? If it still requires more compute. This way, every process will get a fair share of compute resources and nothing gets starved. This is very, very important. Again, here, very importantly, if you think about it, this is a very good algorithm, but the challenge here is, how do you decide what is the right time quanta or time slice? That's an important question to think about, right? What should be the right quanta or the right slice of time? Because there are different processes. Different processes require different resources. So how does performance change as you change your time quanta or time slice? Right? Very important. If your time quanta is very, very small, if your time quanta is, let's say, 0.1 milliseconds or something very, very small, then what happens? If it's very small, there is lots of context switching. There is tons of context switching. If it is very small, you end up spending a lot of time in context switching itself, because every few milliseconds or microseconds, you're just going from one process to other process. Again, context switching does take some time. Context switching is not that trivial. It takes some amount of time. But if you have too much of context switching, there is no progress. Okay, your efficiency becomes close to zero. Your efficiency is very low. Your efficiency is low. What do I mean by efficiency? Your throughput is low. If your time quanta is very small, it's not good. If your time quanta is very large, let's assume my time quanta is, let's say, instead of 2, my time quanta is 10. Then how does this behave? This behaves like first come, first serve, right? Then this basically behaves like first come, first serve. If time quanta is very large, let's assume in this case time quanta is 10. Then first I will schedule P1, then P2, then P3, because that's the order in which these processes are getting queued, right? If you think about it. So what is important here is, in the worst case, if your time quanta is too large, your round robin becomes equivalent to FCFS. This is very important, right? If it is, again, if it is large, there is lesser amount of context switch. There is lesser context switch. But what could happen is, if this is too large, your responsiveness might degrade. Your responsiveness might suffer. Responsiveness could suffer. For example, again, this is not very large. This is large. For example, imagine if I have a process which requires a lot of like a GUI process, where I'm moving the mouse and the mouse movement should be clearly visible, like this software in which I'm recording everything, right? So as I move my mouse, look at this. As I move my mouse, it should immediately be seen on the screen, right? So if I want highly responsive graphic or GUI based systems, if I have large time quanta, they will not feel responsive. They'll look very sluggish and slow, right? But if you have too small, there is of course context switching. Okay, if it is too small, it's dangerous. But if it is small, there are more context switches. It improves responsiveness. So improvement in responsiveness. Again, there are lots of types of processes, right, that an operating system runs. If you think about it, there are some OS processes which do not require that much of compute resources, which complete very fast, which are not GUI based, or which are not interactive, or which require a lot of responsiveness. There are some backup processes which require a lot of compute and IO, where we don't, again, there are different types of processes, unfortunately, in operating system. So choosing the right time quanta is not an easy challenge. Okay, because if you keep it too small, this is terrible. This also basically becomes equivalent to FCFS. Now we have to choose between small and large. Again, sometimes you may have a GUI responsive process. Sometimes you may not have a GUI responsive process. Then what do you do? So what is the right time quanta? Deciding that is one of the major challenges in a round robin based algorithm implementation in a real operating system. That's a huge challenge. So there are some workarounds for this. Okay. So there is this. Okay. So let's solve a problem before we go into the next algorithm. Okay. There is this interesting problem that we can solve. Suppose, imagine if I have 4 processes A, B, C, D, all of them have the same arrival time. But we are told that A came into the queue before B few milliseconds. Okay, so what does my ready queue look like? My ready queue, A comes first, then comes B, then comes C, then comes D. Okay, they came, see their arrival time is the same, but A came slightly before B, slightly before C, B came slightly before C came slightly before D. So in the ready queue, this is how they are queued up. Now the question here is the time quanta is 1 unit. What is the completion time of process A? Okay, so let's see this. Actually, let's draw the Gantt chart also here. Okay, so let me draw the Gantt chart also here. Okay, so I'll also keep my ready queue here. This is my CPU. So I'll start with A, right? So A, I can only get 1 unit of time. So A gets scheduled for 1 unit of time, right? It still has 3 units of compute that it still needs. So it gets queued at the end. Cool. Next, B. In the queue, what do we have? We have B. B requires only 1 unit of time. So B completes very quickly. So B is completed now. What about C? C requires 8 units of time. Okay. So C gets, again, so B is complete, so we don't add it back to the queue. C requires 8 units of time. We give it 1 unit of time, right? 7 more units left. So C gets added to the back of the queue. Very good. So what is our question? Our question is, what is the complete time of A? So let's see that. Okay. So C, 7 more units left. D. What happens to, so C is done. Now I have D. Okay. So I remove D from the ready queue. I give it 1 unit of time, 1 unit of time on the CPU. D completes. So D does not get. Now we have only A and C in the queue. Now A gets its turn. Okay. Obviously A gets its turn, but A can only get 1 quanta of time or 1 unit of time. So A still requires 2. So A gets added back to the queue. Now I have C. C gets 1 unit of time, right? C gets 1 unit of time. Very good. But C is not yet done. So C gets added back to the queue. Now A again gets its turn, right? A again gets its turn. A requires 1 more unit of time. So it adds itself to the back of the queue. C still has 6. So we give C a chance, right? So 5 more units left for C, right? Now I have A again. Right, so C also gets added back to the queue because C has 5 more units of compute time that it needs. So I remove A, I plug A here, right? I plug A here. So this is 8, so this will be 9. So now A is complete. Now A is complete. Okay, so A doesn't get added. Now you keep having C, so on and so forth till the time C completes. So what is the complete time of A? Complete time of A is equal to 9. Okay, very simple question, but you have to be careful. You have to understand how the round robin works. You have to be careful with the ready queue and drawing the Gantt chart. Once you do both of them, it's very easy to observe that in a round robin. Again, we are talking about round robin here. In a round robin system, very simple. The complete time of A is 9. Okay, we don't have to work out what happens for C because that's not being asked here. Okay, very good. But it's very simple to see that there is no other process right now. So you'll keep having C which executes again and again and again and again, right? Very simple. So there is this next idea called as multi-level queues. Again, here, if you notice in round robin, we said there are lots of types of processes. Why are we trying to jumble up, or why are we trying to merge all processes and put all processes in a single ready queue, right? Why are we trying to use a single algorithm for each of them? Because each of them has their own requirements. A GUI process or an interactive process has a very different requirements as compared to a backup process, which has very different requirements to an OS process, which has very different requirements from a background process, right? So there are tons of types of processes. So what multi-level queue says is, let's have multiple ready queues, one ready queue corresponding to each type of process. So this ready queue could be for OS processes because OS processes are fairly important. So let's do that. Then comes all interactive GUI, so interactive processes. Then we do all background processes, which are not very important or critical to be interactive. Then finally, we can have something like a backup process, right? A backup process or a virus check process, which is not too critical to run very quickly. So the way it works is, again, each of these ready queues, look at this. These are called multi-level queues because they're so this is a multi-queue system. Okay. So you have multiple ready queues here. This is also called as multiple ready queue system. Okay, just like it's called multi-level queues, the alternative name is multiple ready queue algorithm. Okay, so the way it works is very interesting. The way it works is, if there is any process in this queue, we schedule it first. If this queue is empty, then we schedule these processes. If this queue is empty, we schedule these processes. so on and so forth. This is the final set of processes which get a turn. So we are actually creating a priority of sorts. Look at this. We are creating a priority of sorts based on the type of the process. If the process is a OS process, it gets the first priority. So multi-level queues give a priority based on the type of the process. And within this OS processes, I can use any algorithm I want. I can use something like round robin here, right? For interactive, again, I can use let's say priority based scheduling, right? The final process here, this will be FCFS. It's very important to realize that this is FCFS, okay, which is non-preemptive, okay? Because if again, this backup process, this is a background process, right? Or a backup process, right? So you have all these processes, and the way it typically works is this. First, you check if this queue is empty. If this queue is empty, only then the interactive processes get a chance. If this queue is empty, only then this gets a chance, and so on and so forth. So you're creating an artificial priority here, where you're saying OS processes get the highest priority. Within OS processes, I'll apply whatever algorithm I want, like round robin. Again, within interactive, again, I will use something like a priority based scheduling. Within background, I can use, let's say, shortest job first, or whatever I want, right? So within each of these queues, I can use any algorithm I want, but I'm creating an artificial priority based on the type of the process. Obviously, there is a problem here. There is a problem of starvation. Obviously, right? There is a problem of starvation. Imagine continuously if I have OS processes or interactive processes, backup processes will never get a turn. Because imagine in modern operating systems, even on Android or Windows or Linux, anything, there is always some interactive component that is running because people are continuously using their mouse and keyboard and things like that. There is a GUI process that is continuously running. So if you keep using this simple multi-level queue, the backup processes and background processes will never get a chance at all. They would never get a chance, right? So starvation of processes which are there lower in this multi-level queue is very possible. So what is the workaround for this? Seems logical, right? Again, here there is one advantage of multi-level queue, which is again, unlike your round robin like strategy, we are giving more priority to operating system processes than interactive. So this is combination of priority across types, and within each type I can use whatever algorithm I want. But starvation is a very real issue here. So how do I get rid of the starvation problem now? Huge drawback is starvation. So then there is something called as multi-level feedback queues. These are very interesting. Okay. So this is a modification of round robin. So this is basically round robin. This is round robin plus multi-level queues. Very interesting strategy. Look at this. If I have a new process, imagine if I have a new process, this process gets added to my ready queue 1. Anything that is there in this ready queue 1, this follows round robin with a time quanta of only 2 units of time. Look at this. It follows with 2 units of time. So every process is given 2 units of time. So we do know that OS processes typically require significantly lesser amount of compute time. So what happens to OS processes? OS processes might require 1 or 1.5 or probably less than 2 units of time. So they'll complete very quickly. So we are not blocking OS processes anyway. But if a process is not completed by the time this 2 units of time is over, it gets queued into a second queue. Look at this. It gets queued into the second queue, which is called as RQ2. This ready queue 2 has a slightly larger time quanta. If you notice, this has time quanta 2, this has time quanta 4, this has time quanta 6, and so on and so forth. The last queue here has simply FCFS with non-preemptiveness. Okay, so look at this. So a typical process joins this queue. If it can finish in 2 seconds, it will finish because it is guaranteed to get at least 2 seconds. Okay, it gets 2 units of time or 2 seconds of compute time for sure. If it finishes, done. So typically OS processes will finish here. If they do not finish, they'll get again tagged. They'll join in this queue. Now, when they join this queue also gets its own time. Okay, then they start executing. Here they get 4 seconds. Here they get 4 units of time. So 2 units plus 4 units. If a process can finish within 6 units, 2 plus 4, that's it. It's done. It doesn't go back to the next queue. So there are some processes like backup processes, like virus detection, right? On your Windows or on your Mac or Linux, etc., or even on your Android. So these take significantly more time. So they will start here. They'll get some compute time, but they'll get added to this queue because they need more time. They could get added to the next queue also, so on and so forth, right? So this strategy is trying to balance between not having starvation. Again, this is not guaranteed to have, this is not always, so this does not guarantee no starvation. Starvation can still happen. Starvation can still happen. Starvation can still happen in this, okay? But you're reducing the chances of starvation. You're just, because you're giving ample amount of time for each process. First you're giving it 2 units of time, then 4 units of time, then 8 units of time, and so on and so forth. In the worst case, we'll say, okay, so this has tried enough number of times, we'll just do it first come first serve with non-preemptiveness. So one more important aspect here is, just like your multi-level queues, so we have understood the round robin aspect of it, right? What is a multi-level queue aspect of it? So just like in your multi-level queues, only when this queue is empty, do processes in this queue get scheduled. Okay, that's very important. Okay, only when this queue is empty, if this queue is empty, only then these processes get scheduled. Only when this queue is empty, do processes in this queue get scheduled. That's very important. So that's what we are borrowing from the concept of multi-level queues. But we also have round robin here, because each of these queues internally uses a round robin except for the very last one. So how can starvation happen? Imagine continuously I'm getting processes. Continuously I'm getting processes. I mean, like that happens a lot in real operating systems, right? Imagine if I have a burst of OS processes that come in. Okay, suppose if I have, let's say, a backup process. The backup process got 2 seconds, then it got 4 seconds. Suppose it is in this queue. Suppose there is a backup process here. When will this queue start executing? Only when this queue is empty and this queue is empty. But what if I keep getting a burst of OS processes now? Hundreds of OS processes. They will, again, OS processes will also complete fast. But this queue is not empty, which means this queue will never get scheduled. Processes in this queue, at the front of this queue, will never get scheduled, which means processes in this queue also will not get scheduled. So starvation can still happen, but we are reducing the chance of starvation to some extent. We are not completely avoiding starvation here. But just like, again, but here what's happening here is, processes like OS processes, which require significantly lower amount of compute resources, do get their turn first. Okay, processes which require a lot of time, like backup processes or virus checks, go lower in the pool, but they do get some time. They've gotten 2 units of time here, they've gotten 4 units of time, they've gotten 6 units of time. But even if after all of this it's not sufficient, then they could get stuck in a thing like this. Okay, so starvation might still happen, it could happen, but this is significantly better than your standard multi-level queues. That's all I wanted. So because we are using some of the advantages of round robin, and again remember that we are typically in practice, we increase the time quanta from one queue to the next queue. So 2, 4, 6, 16, whatever, just keep increasing this, so that when a process which is there in this queue gets scheduled, because it cannot complete in 2 seconds or 4 seconds, it gets slightly more time now. Okay, we are allowing it more time because we don't have processes in these 2 queues. So we are trying to blend both round robin and multi-level queues to create something called as multi-level feedback queues. And these are called feedback queues because of these connections. These are your feedback connections here, right? So I hope you got a good sense of all the scheduling algorithms. Again, no scheduling algorithm is perfect. Every scheduling algorithm has its own advantages and disadvantages. Okay, the appropriate choice of which scheduling algorithm to use depends on the operating system that you're designing, right? As I mentioned to you, priority based scheduling is something which is very common, which is used extensively in operating systems like Linux and Android. And that too, it has components of both static priority based scheduling and dynamic priority based scheduling, because the OS has much more control on how to write the rules, how to age, right, to change the priority of each process and things like that. Because this gives a lot of control to the operating system. That's why priority based scheduling is so popular in Linux and Android like operating systems.